The expansion of the universe is one of the most profound and complex mysteries in cosmology. It raises questions about the origin, structure, and eventual fate of the cosmos, compelling scientists, philosophers, and curious minds to explore the very nature of space, time, and the universe itself. The discovery that the universe is not static but expanding has reshaped our understanding of the cosmos, forcing us to rethink the very fabric of reality and the laws that govern it. To understand the universe's expansion, we must go back to the early 20th century. At that time, many scientists, including Albert Einstein, believed in a static universe, one that neither expands nor contracts. Einstein even introduced a cosmological constant to his equations of general relativity to maintain this idea of a steady-state universe. However, this assumption was soon challenged by Edwin Hubble's groundbreaking discovery in the 1920s. By observing distant galaxies, Hubble found that these galaxies were moving away from us, and the farther away they were, the faster they seemed to be receding. This phenomenon, known as Hubble's law, provided strong evidence that the universe was, in fact, expanding. This expanding universe led to the development of the Big Bang theory, which posits that the universe began as a singular point, an infinitely dense and hot state, before it rapidly expanded. The idea that all matter and energy in the universe originated from a single point and has been expanding ever since is mind-boggling, and it raises numerous questions about the nature of the universe itself. What existed before the Big Bang? What caused the expansion to begin? And how will the expansion evolve in the future? One of the most intriguing aspects of the universe's expansion is the fact that it is accelerating. For much of the 20th century, cosmologists believed that the expansion would slow down due to the gravitational pull of all the matter in the universe. Some even theorized that the expansion might eventually reverse, leading to a big crunch, where the universe collapses back in on itself. However, in the late 1990s, observations of distant supernovae revealed that the expansion was not slowing down but speeding up. This discovery was so unexpected that it earned the Nobel Prize in Physics for the scientists involved. The cause of this accelerated expansion is attributed to what we now call dark energy, a mysterious force that makes up about 70% of the universe. Dark energy is thought to act like a kind of anti-gravity, pushing galaxies apart and causing the expansion of the universe to accelerate over time. Despite its profound influence on the cosmos, dark energy remains one of the greatest mysteries in physics. We don't know what it is, where it comes from, or how it operates. Some theories suggest that dark energy might be a property of space itself, while others propose that it could be a manifestation of some new, unknown force. The expansion of the universe also has profound implications for the ultimate fate of the cosmos. If the universe continues to expand at an accelerating rate, we could be heading towards a scenario known as the Big Freeze. In this scenario, galaxies will drift farther and farther apart, stars will eventually burn out, and the universe will become a cold, dark, and empty place. Alternatively, some theories propose that the accelerating expansion could eventually lead to a Big Rip, where the force of dark energy becomes so strong that it tears galaxies, stars, and even atoms apart. Another possibility is the concept of a cyclic universe, in which the universe undergoes a series of expansions and contractions, with each cycle beginning with a big bang and ending with a big crunch. While this idea has been explored in various forms over the centuries, modern versions of the cyclic universe theory attempt to reconcile the expansion of the universe with other concepts like quantum mechanics and string theory. If the universe is indeed cyclical, it raises intriguing questions about the nature of time and whether our universe is just one in an infinite series of expansions and contractions. The idea of the universe's expansion also brings into focus the concept of the observable universe. Due to the finite speed of light and the fact that the universe is only around 13.8 billion years old, there is a limit to how much of the universe we can observe. This observable universe, with a radius of about 46 billion light-years, represents the portion of the universe from which light has had time to reach us. Beyond this observable horizon lies a vast expanse of space that we will never be able to see or explore, as the accelerating expansion of the universe is driving distant galaxies away from us faster than the speed of light. In recent years, the study of cosmic inflation has added another layer of complexity to our understanding of the universe's expansion. According to the theory of inflation, the universe underwent a brief but extremely rapid expansion in the first fractions of a second after the Big Bang. This period of inflation helped to smooth out the universe, explaining why the cosmos appears so uniform on large scales, with galaxies distributed relatively evenly throughout space. Inflation also helps to explain the small fluctuations in the cosmic microwave background radiation, which are believed to be the seeds of galaxies and other large-scale structures in the universe. One of the most fascinating consequences of the universe's expansion is the possibility of a multiverse. Some versions of inflation theory suggest that our universe might be just one of many in a vast multiverse, with each universe expanding from its own Big Bang event. These other universes could have different physical laws, constants, and structures, making them vastly different from our own. While the multiverse remains a speculative idea, it has captured the imagination of many scientists and has profound implications for our understanding of the universe and our place within it. The expansion of the universe also raises profound philosophical and existential questions. If the universe is expanding, what does that mean for our understanding of time and space? Is the universe infinite, or does it have an edge? If the universe has a beginning, does it also have an end? And what role, if any, do we as conscious beings play in this vast, expanding cosmos? In addition to these philosophical questions, the expansion of the universe has practical implications for our understanding of fundamental physics. The study of the universe's expansion has led to new insights into the nature of gravity, quantum mechanics, and the fundamental forces that govern the cosmos. It has also spurred the development of new technologies and techniques for observing distant galaxies and measuring the expansion of the universe with greater precision. As our understanding of the universe's expansion continues to evolve, new discoveries and breakthroughs will likely reshape our understanding of the cosmos. With advanced telescopes and space missions, scientists are uncovering new clues about the nature of dark energy, the structure of the universe, and the forces driving its expansion. These discoveries not only deepen our knowledge of the universe but also raise new questions and challenges for future generations of scientists to explore. The mystery of the expanding universe is far from solved, and it is likely that we are only beginning to scratch the surface of this profound cosmic puzzle. The more we learn about the universe's expansion, the more we realize how much we don't know. But it is this sense of wonder and curiosity that drives us to keep exploring, to keep asking questions, and to seek a deeper understanding of the cosmos and our place within it. The notion of the expanding universe has also brought new ideas into focus regarding the structure and composition of the cosmos. It forces us to grapple with the vast distances and scales involved, where light itself takes millions or even billions of years to traverse the gulf between galaxies. One of the consequences of this expansion is the redshift phenomenon, which provided a critical clue about the nature of the universe's expansion in the first place. Redshift occurs because, as the universe expands, the wavelengths of light emitted from distant objects are stretched, causing them to shift toward the red end of the spectrum. This was the key observation that allowed Edwin Hubble to conclude that galaxies are moving away from us, and that the universe is getting bigger. The greater the redshift, the faster the object is moving away, which leads directly to the conclusion that distant galaxies are receding at greater speeds. This relationship between redshift and distance is a fundamental tool for cosmologists in determining the size and scale of the universe. As the universe expands, space itself is stretching, which gives rise to the intriguing concept that it's not just galaxies moving through space, but space itself expanding. This distinction is crucial in understanding how the universe works on large scales. Imagine space as a balloon and galaxies as dots on its surface. As the balloon inflates, the dots move away from each other, not because they are traveling across the surface, but because the surface itself is expanding. This simple analogy captures the essence of cosmic expansion, but the reality of it is far more complex and enigmatic. One of the curious consequences of this expansion is that, over time, distant galaxies will become invisible to future astronomers. As the expansion accelerates, more and more galaxies will be carried beyond the cosmic horizon, the point beyond which light from those galaxies can no longer reach us. This means that in billions of years, future civilizations may look up at the night sky and see only a few nearby galaxies, unaware of the vast universe that once existed beyond their observational reach. This raises interesting questions about the transient nature of our knowledge of the cosmos. Are we living in a special time when the universe is still accessible to us, or will our view of the universe always be incomplete as it continues to expand? Cosmic expansion also plays a pivotal role in shaping the evolution of galaxies, clusters of galaxies, and the large-scale structure of the universe. The universe is not expanding uniformly everywhere, as gravity pulls matter together in some regions while expansion drives it apart in others. This interplay between gravity and cosmic expansion is responsible for the formation of galaxy clusters, superclusters, and the cosmic web, the vast, filamentary structure that makes up the large-scale distribution of matter in the universe. The cosmic web is a delicate balance between gravitational attraction, which pulls matter into denser regions, and the expansion of space, which stretches these regions apart. Over billions of years, galaxies and clusters of galaxies have formed along these filaments, with vast voids of mostly empty space in between. The discovery of this large-scale structure was another milestone in cosmology, revealing that the universe is far more complex and interconnected than we had previously imagined. Despite the vast scales involved, the expansion of the universe has measurable effects on the lives of galaxies, stars, and planets. One consequence of this expansion is that galaxies are gradually drifting farther apart, making collisions between galaxies less common over time. While collisions between galaxies can still happen in the relatively near future, for example, the Milky Way and the Andromeda Galaxy are on a collision course that will result in a merger in a few billion years. Such events will become rarer as the universe continues to expand. Over longer timescales, the expansion of the universe will isolate galaxies, preventing them from interacting with one another and leading to a lonely, isolated cosmos. The expansion of the universe is also intertwined with the concept of entropy, the measure of disorder in a system. According to the second law of thermodynamics, entropy in a closed system always increases over time. As the universe expands and becomes more diffuse, its overall entropy is also increasing. This increase in entropy is driving the universe toward a state of maximum disorder, where all matter and energy will eventually be evenly distributed across vast distances, leading to the so-called heat death of the universe. In this state, no thermodynamic processes can occur, and the universe will essentially be a cold, dark, and static place. However, the exact nature of the universe's future remains uncertain. While the heat death scenario is the most widely accepted outcome, other possibilities exist depending on the true nature of dark energy and the ultimate fate of cosmic expansion. If dark energy is not a constant but instead changes over time, it could lead to very different outcomes for the universe. For example, if dark energy were to weaken or reverse its effects, the universe could stop expanding and eventually contract in a big crunch. Alternatively, if dark energy grows stronger over time, it could lead to the Big Rip, in which the universe's expansion accelerates to the point that galaxies, stars, planets, and even atoms are torn apart. The discovery of the universe's accelerated expansion and the role of dark energy have also challenged our understanding of the fundamental forces of nature. Dark energy seems to behave very differently from gravity, which is attractive and pulls matter together, while dark energy appears to have a repulsive effect, pushing space itself apart. This dichotomy between dark energy and gravity raises deep questions about the nature of the universe and the fundamental forces that govern it. Some theories propose that dark energy might be related to quantum fluctuations in empty space, while others suggest it could be a manifestation of a new force or field that we have yet to discover. The study of the universe's expansion has also led to new insights into the age of the universe. By measuring the rate of expansion, known as the Hubble constant, scientists have been able to estimate the age of the universe at around 13.8 billion years. This is a remarkable achievement, as it allows us to trace the history of the universe back to its earliest moments, providing a timeline for the formation of galaxies, stars, and planets. However, recent measurements of the Hubble constant have led to some discrepancies, with different methods giving slightly different values for the expansion rate. This Hubble tension has sparked debates among cosmologists and could point to new physics beyond our current understanding of the universe. As we continue to probe the mysteries of the expanding universe, new questions and challenges will undoubtedly arise. The discovery of gravitational waves, for example, has opened up a new window into the universe, allowing us to observe cosmic events like the mergers of black holes and neutron stars. These observations provide new ways to test our understanding of the expansion of the universe and could offer new insights into the nature of dark energy, gravity, and the fabric of space-time itself. In addition to gravitational waves, future observations of the cosmic microwave background (CMB) radiation, the faint afterglow of the Big Bang, will continue to shed light on the early universe and the dynamics of cosmic expansion. The CMB provides a snapshot of the universe when it was just 380,000 years old, offering a glimpse into the conditions that set the stage for the formation of galaxies and the large-scale structure of the cosmos. By studying the CMB in greater detail, scientists hope to uncover new clues about the nature of dark energy, inflation, and the expansion of the universe. The expansion of the universe also has implications for the search for extraterrestrial life. As galaxies drift farther apart, the chances of detecting signals from other civilizations may diminish, as the vast distances between galaxies make communication increasingly difficult. If intelligent life exists elsewhere in the universe, the accelerating expansion could make it harder for civilizations to communicate or interact with one another. This raises philosophical questions about the future of life in an expanding universe, and whether our technological achievements will ever allow us to bridge the growing gaps between galaxies. Ultimately, the mystery of the universe's expansion is one that touches on both the smallest scales of quantum mechanics and the largest scales of cosmology. It challenges our understanding of space, time, and the nature of reality itself, forcing us to confront questions about the origins and fate of the cosmos. While we have made remarkable progress in understanding the universe's expansion, there is still much we don't know, and the journey to uncover the full story of the expanding universe is far from over. As scientists continue to explore the mysteries of cosmic expansion, one thing is clear: the universe is far more dynamic, complex, and mysterious than we ever imagined. The discovery that the universe is expanding, and that this expansion is accelerating, has revolutionized our understanding of the cosmos and raised profound questions about the nature of space, time, and the forces that govern the universe. The expanding universe challenges our most fundamental assumptions about the cosmos and forces us to reconsider the ultimate fate of everything within it. As we delve deeper into the mysteries of cosmic expansion, we are confronted with the possibility that the universe we know is only one chapter in a much larger story, one that spans an unimaginable expanse of time and space. One of the central questions in the study of cosmic expansion is the role of dark energy. Dark energy is a mysterious form of energy that is thought to make up roughly 68% of the total energy content of the universe, yet we know very little about it. It appears to be responsible for the accelerated expansion of the universe, but its nature remains one of the biggest puzzles in modern cosmology. Dark energy could be a constant, an inherent property of space itself, in which case the expansion of the universe will continue indefinitely. This concept aligns with what is known as the cosmological constant, a term first introduced by Albert Einstein in his equations of general relativity. Initially, Einstein introduced the cosmological constant to account for a static universe, but after Hubble's discovery of an expanding universe, he discarded the idea, calling it his biggest blunder. However, the resurgence of the cosmological constant in the form of dark energy has given this concept new life, suggesting that it may play a crucial role in shaping the future of the cosmos. If dark energy is indeed a cosmological constant, the universe will continue expanding forever, with galaxies drifting farther apart until they are no longer visible to one another. Stars will eventually burn out, black holes will evaporate, and the universe will slowly fade into darkness, a scenario often referred to as the Big Freeze, or Heat death. In this scenario, the universe approaches a state of maximum entropy, where no usable energy remains to fuel stars, galaxies, or life. While this outcome may be billions of years in the future, it is a sobering reminder of the impermanence of the cosmos. However, there are other possibilities for the fate of the universe, depending on the nature of dark energy and how it evolves over time. Some theories suggest that dark energy might not be a constant but could change in strength over time. If dark energy were to weaken, the expansion of the universe might eventually slow down or even reverse, leading to a big crunch. In this scenario, gravity would eventually overpower the repulsive force of dark energy, causing the universe to collapse in on itself. Galaxies, stars, and planets would be pulled closer together, culminating in a cataclysmic event where the universe shrinks to a singularity, potentially resetting the cosmic cycle. Another possibility is the Big Rip, a more dramatic outcome in which dark energy grows stronger over time. If dark energy continues to accelerate the expansion of the universe, it could eventually reach a point where even the fundamental forces that hold atoms and molecules together are overwhelmed. In this scenario, the fabric of space-time itself would be torn apart, resulting in the disintegration of galaxies, stars, planets, and ultimately even atoms. The Big Rip would represent the ultimate destruction of the universe, as the very structure of matter is ripped asunder. The future of the universe hinges on understanding the true nature of dark energy, and this has led scientists to explore a range of possibilities. Some researchers have proposed that dark energy could be linked to quantum fluctuations in the vacuum of space. According to this idea, the energy associated with these fluctuations might be responsible for the accelerating expansion of the universe. This concept connects the behavior of the universe on the largest scales with the strange and unpredictable world of quantum mechanics, hinting at a deeper relationship between the two. Other theories suggest that dark energy could be a new, unknown field or force that we have yet to fully understand. Some physicists have proposed that dark energy could be related to a scalar field, similar to the Higgs field, which permeates the universe and affects its expansion. If such a field exists, its properties could change over time, potentially leading to different outcomes for the universe's expansion. This idea ties into broader efforts to develop a theory of everything, a unified framework that combines general relativity, which describes gravity and the large-scale structure of the universe, with quantum mechanics, which governs the behavior of particles on the smallest scales. The discovery of the accelerated expansion of the universe has also sparked new interest in the concept of the multiverse. Some cosmologists have suggested that our universe might be just one of many, each with its own physical laws and constants. In this view, dark energy could vary from one universe to another, leading to different rates of expansion and different fates for each universe. The multiverse hypothesis remains highly speculative, but it offers a tantalizing glimpse into a much larger and more complex reality than we currently understand. One of the key tools in studying the expansion of the universe and the role of dark energy is the cosmic microwave background (CMB) radiation. The CMB is the afterglow of the Big Bang, a faint radiation that fills the universe and provides a snapshot of the cosmos when it was just 380,000 years old. By studying the CMB, scientists can gain insights into the early universe and the processes that shaped its evolution, including the expansion of space. The CMB also provides a way to test different models of dark energy and cosmic expansion. By comparing observations of the CMB with predictions from different cosmological models, researchers can refine their understanding of the universe's expansion history and the behavior of dark energy. Future observations of the CMB, combined with data from other sources such as supernovae and large-scale galaxy surveys, will continue to play a crucial role in unraveling the mysteries of cosmic expansion. In addition to the CMB, other phenomena such as gravitational waves offer new ways to probe the expansion of the universe. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as the merging of black holes or neutron stars. The detection of gravitational waves has opened up a new era in astronomy, allowing scientists to observe events that are invisible to traditional telescopes. Gravitational waves can also provide new insights into the expansion of the universe, as they offer a different way to measure distances and test the behavior of space-time on large scales. The study of cosmic expansion also intersects with the field of dark matter, another mysterious substance that makes up roughly 27% of the universe's total energy content. While dark matter does not directly affect the expansion of the universe in the same way that dark energy does, it plays a crucial role in shaping the formation of galaxies and the large-scale structure of the cosmos. Dark matter is thought to be a type of particle that interacts only through gravity and not with light, making it invisible to telescopes. However, its gravitational effects can be observed in the motion of galaxies and the bending of light around massive objects, a phenomenon known as gravitational lensing. The interaction between dark matter, dark energy, and the expansion of the universe is one of the most exciting frontiers in cosmology. As we learn more about these enigmatic components of the cosmos, we may uncover new laws of physics that govern the behavior of the universe on both large and small scales. The search for dark matter particles, the study of gravitational waves, and the exploration of the cosmic microwave background are all part of a broader effort to understand the fundamental nature of the universe and its expansion. As we look to the future, new experiments and observations will continue to refine our understanding of the expanding universe. The next generation of telescopes, such as the James Webb Space Telescope and the European Extremely Large Telescope, will allow astronomers to observe the universe in unprecedented detail, providing new data on the behavior of galaxies, the large-scale structure of the cosmos, and the nature of dark energy. These observations, combined with theoretical advances in fields such as quantum mechanics and string theory, may help unlock the secrets of cosmic expansion and the ultimate fate of the universe. In the meantime, the expanding universe serves as a powerful reminder of the vastness and complexity of the cosmos. It challenges us to think on scales of time and space that are difficult to comprehend, and it raises profound questions about the nature of reality and our place in the universe. The discovery that the universe is not static but is continually evolving has reshaped our understanding of the cosmos and opened up new avenues of exploration and discovery. The expanding universe, with all its mysteries, forces us to grapple with questions that touch on both the origin of everything and the ultimate fate of all existence. As we continue to study the cosmos, we find that the story of the universe's expansion is not just about the physical processes involved, but also about the profound philosophical and existential implications it holds. One of the key concepts tied to the universe's expansion is that of cosmic inflation, which posits that the universe underwent a rapid expansion in the first fractions of a second after the Big Bang. This inflationary period is thought to have expanded the universe at a rate far exceeding the speed of light, smoothing out any irregularities and explaining the large-scale uniformity we observe in the cosmic microwave background, CMB, radiation today. Cosmic inflation provides an elegant solution to several long-standing puzzles in cosmology, such as the horizon problem, which questions how different regions of the universe could be so similar when they are too far apart to have communicated with each other through the exchange of light or any other signal. The inflationary model suggests that these regions were once much closer together before the rapid expansion, explaining their uniformity. Additionally, inflation accounts for the flatness problem, which refers to the surprising fact that the universe appears to be geometrically flat, meaning its curvature is very close to zero. Inflation stretched the fabric of space to such an extent that any initial curvature would have been smoothed out, much like how a balloon flattens as it is inflated. Despite its success in explaining many features of the universe, cosmic inflation raises its own set of questions. What caused inflation to start, and what mechanism brought it to an end? Some theories suggest that inflation is driven by a scalar field, known as the inflaton, which caused the rapid expansion of the universe when it transitioned from a higher energy state to a lower energy state. However, the details of this process remain speculative, and the nature of the inflaton field is still unknown. Furthermore, some versions of inflationary theory suggest that inflation may never truly end but could continue in different regions of the universe, leading to what is known as eternal inflation. In this scenario, while inflation may have stopped in our observable universe, it could still be ongoing in other, distant regions. This leads to the intriguing possibility of a multiverse, in which our universe is just one of an infinite number of universes, each with its own laws of physics, constants, and possibly even different forms of matter and energy. The multiverse hypothesis, though speculative, has captured the imagination of cosmologists and physicists alike. If eternal inflation is correct, then it suggests that the universe we observe is just a small bubble in a much larger, ever-expanding cosmic foam, with new universes being born all the time. In some of these universes, conditions may be similar to ours, while in others, the physical constants might be so different that galaxies, stars, and life could never form. The multiverse concept shifts our understanding of the universe from a singular entity to a vast, potentially infinite landscape of possibilities, raising profound questions about the nature of reality itself. One of the challenges with the multiverse hypothesis is that it is difficult, if not impossible, to test. Because other universes would be causally disconnected from our own, we cannot directly observe or interact with them. This has led to debates within the scientific community about whether the multiverse is a legitimate scientific concept or a philosophical idea. Nonetheless, the possibility of a multiverse continues to inspire new lines of inquiry in both cosmology and theoretical physics. Another fascinating aspect of the expanding universe is the concept of the observable universe. Due to the finite speed of light and the fact that the universe is expanding, we can only observe a limited portion of the cosmos, roughly 93 billion light-years in diameter, despite the universe being only 13.8 billion years old. This discrepancy arises because the space between distant galaxies is expanding, meaning that some regions of the universe are moving away from us faster than the speed of light. As a result, there are parts of the universe that we can never observe, no matter how advanced our telescopes become. These unobservable regions may contain galaxies, stars, and even entire clusters of matter that will forever remain beyond our reach. The concept of the observable universe highlights the limits of our knowledge and forces us to confront the possibility that we may never fully understand the true nature of the cosmos. As the universe continues to expand, the light from distant galaxies will eventually redshift beyond the visible spectrum, becoming undetectable to even the most sensitive instruments. In the far future, a distant civilization might look out at the night sky and see only a dark, empty void, unaware that the universe was once teeming with galaxies. This realization underscores the importance of our current era in cosmic history. We live at a time when we can still observe the distant reaches of the universe and gain valuable insights into its structure and evolution. Future generations may not have this opportunity, as the expanding universe gradually erases the cosmic record, hiding distant galaxies behind an ever-growing veil of darkness. The expansion of the universe also has implications for the large-scale structure of the cosmos. Over time, the universe has evolved from a hot, dense state following the Big Bang into a vast, web-like network of galaxies, galaxy clusters, and cosmic filaments. These structures are held together by the gravitational pull of dark matter, which forms a scaffold on which ordinary matter accumulates to form stars, galaxies, and other cosmic objects. The large-scale structure of the universe is shaped by the interplay between gravity, dark matter, and dark energy. On smaller scales, gravity dominates, pulling matter together to form galaxies and galaxy clusters. However, on the largest scales, the repulsive force of dark energy becomes more significant, causing the universe to expand at an accelerated rate and pushing galaxies apart. This cosmic tug-of-war between gravity and dark energy will determine the ultimate fate of the large-scale structure of the universe. As the universe expands, galaxies that are not gravitationally bound to one another will drift farther apart. Over billions of years, the observable universe will become more and more sparse, with distant galaxies receding beyond the cosmic horizon. Galaxy clusters, which are held together by the gravitational pull of dark matter, may remain intact for some time, but even they will eventually succumb to the expansion of space. In the distant future, the universe could become a cold, dark, and desolate place, with only black holes and subatomic particles remaining. One of the most intriguing ideas related to the universe's expansion is the possibility that space itself is not just expanding, but could also be connected to higher dimensions. This idea is central to some theories in string theory and other advanced models of physics, which propose that the universe we experience may be a lower dimensional brane embedded within a higher dimensional space. In this view, the expansion of the universe might be linked to the dynamics of these higher dimensions, offering a new perspective on the nature of space and time. These higher dimensional theories suggest that the forces and particles we observe in our universe might be manifestations of more fundamental entities that exist in higher dimensions. For example, gravity, which is relatively weak compared to the other fundamental forces, could be leaking into higher dimensions, explaining its apparent weakness in our four-dimensional universe, 3 dimensions of space and 1 of time. If these ideas are correct, the expansion of the universe might be just one aspect of a much larger and more complex reality, one that extends beyond the limits of our current understanding. The connection between the expansion of the universe and higher dimensional physics also raises the possibility that the universe could experience different phases of expansion in the future. Some models suggest that the universe could undergo cycles of expansion and contraction, with each cycle corresponding to a different configuration of the higher dimensional space in which our universe is embedded. These cyclical models offer an alternative to the traditional view of a one-time Big Bang followed by eternal expansion, suggesting that the universe could have an infinite past and future, with no true beginning or end. While these ideas are still speculative, they point to the possibility that the expansion of the universe is part of a much larger, more intricate cosmic story, one that involves higher dimensions, new forms of matter and energy, and perhaps even multiple universes. As our understanding of the universe deepens, we may find that the expansion we observe today is just one chapter in an ongoing cosmic evolution that stretches far beyond the limits of human perception. The notion that the universe could undergo cycles of expansion and contraction is a fascinating departure from the standard cosmological model, which suggests a singular beginning with the Big Bang and an indefinite expansion towards a heat-death. This alternative theory, sometimes referred to as the cyclic universe, or Big Bounce model, presents a dynamic and evolving universe that oscillates between phases of growth and collapse, potentially avoiding the paradoxes of a singular origin or an infinite future of ever-expanding emptiness. In the cyclic model, the universe does not have a true beginning or end. Instead, each period of expansion eventually gives way to a contraction phase, leading to a collapse, or Big Crunch, which is then followed by a new expansion. This continuous loop of birth, death, and rebirth of the universe suggests that the Big Bang itself may not have been a singular event, but just one in an infinite series of cosmic cycles. One of the most compelling features of the cyclic universe is that it provides a natural explanation for the low-entropy state of the universe observed after the Big Bang. According to the second law of thermodynamics, entropy, or disorder, tends to increase over time, which raises the question of how the early universe could have been in such a low-entropy, highly ordered state. In a cyclic universe, each new cycle could reset the entropy of the universe, allowing for a low entropy beginning after each Big Crunch. In this way, the universe could experience an endless succession of low entropy beginnings, each following the collapse of the previous cycle. The cyclic model also suggests a different fate for dark energy, the mysterious force driving the accelerated expansion of the universe. In the standard model of cosmology, dark energy is thought to be a constant, leading to an ever-accelerating expansion that eventually results in a cold, empty universe. However, in the cyclic model, dark energy could be a transient phenomenon, linked to the expansion phase of the universe. As the universe expands, dark energy dominates, but eventually, it could decay or transform into another form of energy, leading to the contraction phase. This cyclical behavior of dark energy would allow the universe to oscillate between phases of acceleration and deceleration, rather than expanding indefinitely. While the cyclic model provides an intriguing alternative to the standard cosmological model, it is still speculative and faces several challenges. One of the primary difficulties is finding a mechanism that could cause the universe to transition smoothly from expansion to contraction. In particular, the universe would need to overcome the repulsive force of dark energy, which currently appears to be driving the accelerated expansion of space. Some theorists have proposed that quantum effects or higher dimensional dynamics could play a role in triggering the contraction phase, but these ideas remain highly speculative. Moreover, observational evidence for the cyclic model is currently lacking. The cosmic microwave background (CMB) radiation, which provides a snapshot of the early universe, is consistent with the predictions of the standard inflationary model, but it does not provide direct evidence for a cyclical universe. Future observations of the large-scale structure of the universe, gravitational waves, or other cosmic phenomena may help to distinguish between the cyclic model and the standard model of cosmology. The concept of a cyclic universe raises profound philosophical and existential questions about the nature of time and the ultimate fate of the cosmos. If the universe is truly cyclical, then it suggests that time itself may be infinite, with no true beginning or end. This challenges our conventional understanding of time as a linear progression from past to future, and opens up the possibility that the universe has always existed in some form. In a cyclic universe, the question of what happened before the Big Bang becomes irrelevant, as there is no singular beginning to the universe. Instead, the Big Bang is just one of many transitions between cycles, and the universe may have existed for an eternity before the cycle we currently observe. This idea challenges the traditional view of the universe as having a finite age and raises the possibility that the cosmos has been undergoing cycles of birth and rebirth for an infinite amount of time. The implications of a cyclic universe also extend to our understanding of the future. In the standard model of cosmology, the universe faces a bleak future, with the eventual heat death, leaving behind a cold, dark, and empty cosmos. In contrast, the cyclic model offers the possibility of renewal, with each contraction phase leading to a new beginning. While individual civilizations, stars, and galaxies may still come to an end, the universe itself could continue to evolve and change, undergoing cycles of destruction and creation. However, even in a cyclic universe, the question of what drives these cycles remains open. Are they governed by fundamental laws of physics that we have yet to discover, or are they the result of deeper, underlying processes that transcend our current understanding of the cosmos? The answers to these questions may lie in the realm of quantum mechanics, string theory, or even entirely new frameworks of physics that have yet to be developed. String theory, in particular, offers some intriguing possibilities for understanding the cyclical nature of the universe. In string theory, the fundamental building blocks of the universe are not point-like particles, but rather one-dimensional strings that vibrate at different frequencies. These strings exist in a higher dimensional space, known as the bulk, which may contain additional dimensions beyond the familiar 3 dimensions of space and 1 of time. Some versions of string theory propose that our universe is a 3-dimensional brane that exists within this higher dimensional bulk. In this view, the universe's expansion and contraction could be driven by interactions between our brane and other branes in the bulk. Collisions between branes could trigger a Big Bang-like event, leading to the expansion of the universe, while subsequent interactions could cause the universe to contract, leading to a cyclical pattern of expansion and contraction. These ideas, while speculative, offer a tantalizing glimpse into the possible connections between higher dimensional physics and the large-scale structure of the universe. If string theory or other higher dimensional models prove correct, they could provide a deeper understanding of the forces driving the expansion of the universe and offer new insights into the nature of space, time, and reality itself. The expanding universe, with its cycles, its potential higher dimensional connections, and its dark energy-driven acceleration, presents one of the most profound mysteries of modern science. Every new discovery deepens our understanding, yet it also reveals new layers of complexity that challenge our assumptions and push the boundaries of human knowledge. As we continue to explore the universe and refine our models of its expansion, we may one day uncover the true nature of the forces shaping the cosmos. Whether the universe continues to expand forever, undergoes cycles of rebirth, or is part of a much larger multiverse, the journey to uncover the mysteries of space promises to reshape our understanding of existence and our place within the vast, ever-changing cosmos. One of the most compelling aspects of universe expansion is its relationship with time. Since the expansion is ongoing, the very nature of time itself becomes an enigma intertwined with the fabric of space. In cosmology, time is closely connected to the rate of expansion. As the universe grows, time as we experience it progresses forward. However, there are still mysteries about whether time has always existed or if it began with the universe. The concept of time starting at the Big Bang is a commonly accepted notion in modern cosmology, primarily supported by the idea that time is inseparable from space. Before the Big Bang, neither time nor space as we know it would have existed, meaning the familiar clock only started ticking with the birth of the universe. This view is linked to the theory of general relativity, where time and space form a four-dimensional continuum. Space-time is affected by the distribution of matter and energy in the universe, which, in turn, affects the rate at which time progresses. However, the possibility of cyclical expansion and contraction, as we discussed earlier, brings new layers to the question of time. If the universe is cyclic, time may extend infinitely into both the past and the future, without a true beginning or end. Each cycle of expansion and contraction would see time reset, or perhaps progress in a different manner during different phases. This challenges the widely held notion of time as linear and makes us wonder about the very nature of temporal existence. Could there be a period of time, or some sort of altered time, where our familiar understanding of cause and effect doesn't apply? Quantum mechanics, the study of the smallest particles in the universe, also adds another dimension to the conversation about the expansion of the universe and its implications for time. At the quantum level, the familiar laws of classical physics break down, and particles can behave in strange and unpredictable ways. One particularly interesting feature of quantum mechanics is the concept of quantum entanglement, where particles that are separated by vast distances can instantaneously affect each other's state. This phenomenon seems to defy the limits of time and space and has led some to speculate that the universe's expansion could be related to deeper, quantum-level processes that we are only beginning to understand. Theories of quantum gravity, which attempt to unify general relativity with quantum mechanics, are especially important in the context of the early universe and its expansion. In the moments following the Big Bang, the universe was incredibly small and dense, and quantum effects would have played a significant role in shaping its development. One of the challenges of modern physics is figuring out how to reconcile the behavior of the universe on the largest scales, governed by general relativity, with its behavior on the smallest scales, governed by quantum mechanics. These two theories are currently incompatible, but a successful theory of quantum gravity could unlock new insights into how the universe expanded from a singularity into the vast cosmos we see today. Some researchers believe that quantum fluctuations in the very early universe could have been responsible for seeding the large-scale structures we observe in the cosmos today, such as galaxies and galaxy clusters. These fluctuations would have been amplified by the process of cosmic inflation, which caused the universe to expand exponentially in a fraction of a second after the Big Bang. The details of how inflation worked, and whether it was driven by a specific particle or field, remain major unsolved questions in cosmology, but it is clear that the rapid expansion of the universe during this period played a key role in shaping its current structure. Another quantum-related mystery linked to universe expansion is the nature of the quantum vacuum. In quantum field theory, the vacuum is not truly empty but is instead filled with fluctuating fields that give rise to virtual particles popping in and out of existence. Some theorists propose that these vacuum fluctuations could be connected to the energy driving the expansion of the universe, possibly explaining the behavior of dark energy. While this idea is still speculative, it shows how the smallest scales of the universe may hold the key to understanding the largest scales of cosmic expansion. There is also the ongoing question of what, if anything, lies beyond the observable universe. The observable universe is limited by the distance that light has been able to travel since the Big Bang, roughly 93 billion light-years in diameter. However, the actual size of the universe could be much larger, and in some models, it could be infinite. The observable universe is constantly expanding, meaning that over time, we will be able to see more of the universe as light from more distant regions reaches us. However, because the universe's expansion is accelerating due to dark energy, there is also a cosmic event horizon, beyond which objects are receding from us faster than the speed of light. Anything beyond this horizon will forever remain inaccessible to us, even though it continues to exist. This idea of an expanding event horizon introduces another mystery related to the long-term fate of the universe. As the expansion continues and the event horizon shrinks, galaxies that are currently visible will eventually disappear from view, receding beyond our ability to detect them. In the far future, the universe could become a dark and lonely place, where only the nearest galaxies remain visible, and the rest of the cosmos fades away into the void. This raises profound questions about the ultimate fate of matter, energy, and information in the universe. Some theorists have proposed that the expansion of the universe could lead to the Big Rip, a scenario where the acceleration continues to increase, eventually tearing apart galaxies, stars, planets, and even atoms. In this model, the universe would end in a violent disintegration, with space itself being torn apart at the seams. The Big Rip is just one of several possible outcomes for the universe's expansion, alongside the Big Freeze and Big Crunch scenarios we have already discussed. One of the most tantalizing mysteries related to universe expansion is the possibility of a multiverse. The multiverse hypothesis suggests that our universe is just one of many, each with its own set of physical laws and constants. In some versions of this theory, the expansion of the universe could create bubbles of space-time, each representing a different universe with its own unique properties. These bubble universes could be expanding and evolving in parallel to our own, but they would be fundamentally disconnected from us, lying beyond our event horizon. In some models of the multiverse, the process of inflation could be eternal, with new universes being created continuously in a never-ending cycle of expansion. This eternal inflation scenario suggests that our universe is just one small part of a much larger and more complex structure, where new universes are constantly being born and expanding into their own regions of space-time. This raises the question of whether the laws of physics as we understand them are truly universal, or if they are just one possibility among many. The multiverse hypothesis also has profound implications for our understanding of the fine-tuning of the universe. Our universe appears to be finely tuned for life, with the physical constants and laws of nature being just right to allow for the existence of stars, planets, and biological organisms. If the multiverse exists, then it could provide an explanation for this fine-tuning. In a vast number of universes, each with different properties, it is inevitable that some universes will have the right conditions for life to arise. We just happen to live in one of those universes. The idea of the multiverse is still highly speculative, and there is currently no direct evidence for its existence. However, it is a logical extension of some of the most well-established theories in modern physics, including inflation and string theory. If future observations or experiments provide evidence for the multiverse, it would represent one of the most profound discoveries in the history of science, fundamentally altering our understanding of reality and our place within it. The expansion of the universe, with all its mysteries and complexities, is a window into the deepest questions about the nature of existence. From the role of dark energy and the fate of the cosmos to the possibility of a multiverse, the study of cosmic expansion challenges us to rethink our assumptions about space, time, and reality itself. The mysteries surrounding the expansion of the universe, and all their layers, present an opportunity to reconsider the very fabric of existence. The enigma of dark energy, which seems to fuel the universe's accelerated expansion, remains one of the most perplexing questions in modern science. This strange force is believed to make up approximately 68% of the total energy content of the universe, and yet we know almost nothing about its true nature. Its discovery, in the late 1990s, overturned our prior understanding of the universe, which was based on the assumption that gravity would slow the expansion over time. Instead, we are confronted with the fact that the universe is expanding faster than ever, with no signs of stopping. The concept of dark energy arose from observations of distant supernovae, which were used to measure the rate of expansion of the universe. These supernovae, known as Type I supernovae, are particularly useful for this purpose because they have a consistent brightness, allowing astronomers to accurately calculate their distance from Earth. What astronomers found was unexpected. Instead of the expansion slowing down, as predicted by models of a universe dominated by matter and radiation, it was accelerating. This was a major surprise and led to the hypothesis that some form of repulsive energy, now known as dark energy, was driving the acceleration. There are several competing theories about the nature of dark energy. One possibility is that it represents a cosmological constant, a term that Albert Einstein originally introduced into his equations for general relativity but later discarded. In this view, dark energy is simply a constant energy density that fills space uniformly. As the universe expands, the volume of space increases, but the density of dark energy remains constant, leading to an overall increase in its influence on the expansion of the universe. This is the simplest explanation for dark energy, and it fits well with current observations, but it leaves many questions unanswered. Why does the cosmological constant have the value that it does? Could it change over time, or is it truly constant? Another possibility is that dark energy is not a constant but rather a dynamic field that changes over time and space. This idea is known as quintessence, and it suggests that dark energy could be the result of a new, as yet undiscovered field that permeates the universe. Unlike the cosmological constant, quintessence would evolve over time, potentially leading to changes in the rate of expansion in the distant past or future. The properties of this field could vary from one region of space to another, leading to subtle variations in the expansion rate across the universe. However, no direct evidence for quintessence has been found, and it remains a speculative idea. There are also more exotic explanations for dark energy that challenge our understanding of the fundamental nature of space and time. Some theorists have proposed that dark energy could be a sign that we are living in a higher dimensional universe, where the effects of extra dimensions manifest as the observed acceleration of the universe's expansion. In these models, our universe is a brain, embedded in a higher dimensional space, and dark energy arises from the interactions between our brain and the larger, higher dimensional universe. This idea is closely related to string theory, which posits that the fundamental particles of nature are not point-like but instead are tiny, vibrating strings that exist in multiple dimensions. Other theories propose that dark energy could be a result of the breakdown of our current understanding of gravity. General relativity has been incredibly successful at explaining the behavior of the universe on large scales, but it may not be the final word on gravity. Some alternative theories of gravity suggest that the accelerated expansion could be a sign that our equations need to be modified, particularly when dealing with the vast scales of the universe. These modified gravity theories could offer an explanation for dark energy without the need to introduce new forms of energy or fields. However, testing these theories is extremely challenging, and so far, general relativity continues to pass all observational tests with flying colors. The mystery of dark energy is closely tied to the overall fate of the universe. If dark energy remains constant, as in the case of the cosmological constant, the universe will continue to expand at an accelerating rate. Over time, galaxies will move farther apart, and the space between them will become increasingly empty. This is the so-called Big Freeze scenario, where the universe becomes cold and dark as all the stars burn out and galaxies drift beyond the observable horizon. In this future, the universe would continue to expand indefinitely, but it would become increasingly devoid of energy and structure, ultimately reaching a state of maximum entropy where no useful energy is available to do work. If dark energy is not constant but changes over time, the future of the universe could be very different. In the quintessence model, for example, dark energy could weaken over time, allowing gravity to eventually slow the expansion and reverse it, leading to a big crunch. In this scenario, the universe would collapse in on itself, possibly ending in a singularity similar to the one that gave rise to the Big Bang. Alternatively, if dark energy becomes stronger over time, the universe could end in a big rip, where the expansion accelerates so rapidly that it eventually tears apart galaxies, stars, planets, and even atoms. The precise nature of dark energy will determine which of these futures awaits us, but for now, it remains one of the most significant unanswered questions in cosmology. The accelerating expansion of the universe also has important implications for the observable universe and our ability to study distant objects. As space expands, light from distant galaxies is stretched, increasing its wavelength and causing it to shift toward the red end of the spectrum. This redshift makes it more difficult to observe distant objects, as their light becomes fainter and more spread out over longer wavelengths. Over time, galaxies that are currently visible will move beyond the observable horizon, effectively disappearing from view. In the far future, the observable universe could be limited to just a few nearby galaxies, with the rest of the cosmos receding beyond our reach. This raises philosophical questions about the nature of knowledge and the limits of human understanding. If the expansion of the universe eventually prevents us from observing distant galaxies, will future generations be able to reconstruct the history of the universe? Will they have access to the same information that we do, or will much of the universe's past be lost to them? The accelerating expansion of the universe means that our window of opportunity to study the cosmos is finite, and we are living in a unique era where we can still observe the large-scale structure of the universe. In addition to dark energy, the expansion of the universe also raises questions about the distribution of matter and energy on the largest scales. One of the key discoveries of modern cosmology is that the universe is not evenly distributed. Instead, matter and energy are concentrated in vast structures such as galaxy clusters and cosmic voids. These structures formed over billions of years through the process of gravitational collapse, where regions of slightly higher density in the early universe attracted more matter, eventually forming galaxies, stars, and planets. The large-scale structure of the universe can be studied through surveys of galaxies and the cosmic microwave background, the faint afterglow of the Big Bang. These observations have revealed a cosmic web of filaments and voids, with galaxies and galaxy clusters forming along the filaments and vast empty regions, or voids, in between. This cosmic web is shaped by the interplay between gravity and the expansion of the universe, with dark matter playing a crucial role in the formation of these structures. Dark matter is another major mystery in cosmology, closely related to the expansion of the universe. Like dark energy, dark matter is invisible and does not interact with light, but it exerts a gravitational influence on the visible matter in the universe. Observations of galaxy rotation curves and the motion of galaxy clusters suggest that there is far more matter in the universe than can be accounted for by the visible stars, gas, and dust. This unseen matter, which makes up about 27% of the universe's total mass energy content, is known as dark matter. The nature of dark matter is still unknown, but it is believed to be made up of particles that do not interact with electromagnetic radiation, making them invisible to telescopes. Several candidates for dark matter particles have been proposed, including weakly interacting massive particles, WIMPs, and axions, but so far, no direct detection of dark matter has been achieved. Understanding the nature of dark matter is crucial for explaining the formation of large-scale structures in the universe and for understanding the dynamics of galaxy clusters. The combination of dark matter and dark energy means that only about 5% of the universe is made up of the familiar matter that we can see and interact with. This has led some to describe the universe as a dark universe, where the vast majority of its content is hidden from direct observation. This realization has profound implications for our understanding of the cosmos and our place within it. How can we hope to understand the universe when most of it is invisible to us? What does it mean to live in a universe where the majority of its energy and matter are in forms that we do not yet fully understand? The enigma of dark energy and dark matter serves as a profound reminder of the limitations of human knowledge. While we have made incredible strides in understanding the universe, the fact that 95% of it consists of substances we cannot directly observe reveals the depth of the mysteries that remain. These unseen components not only influence the large-scale structure and expansion of the universe but also challenge our models of physics. Could the solutions to these mysteries involve entirely new physics, or are we missing some key piece that might unite these unknowns with the familiar forces we understand? One of the most fascinating implications of the universe's expansion, combined with the influence of dark energy, is the notion of the observable universe shrinking over time. As the universe expands, distant galaxies move farther away, eventually reaching a point where their light can no longer reach us. This is due to the expansion of space itself, which can eventually outpace the speed of light for very distant objects. This phenomenon creates a cosmological event horizon, a boundary beyond which events can no longer influence us. In practical terms, this means that as time goes on, more and more galaxies will slip beyond the observable horizon, leaving future astronomers with a much smaller slice of the cosmos to study. This shrinking observable universe will limit our ability to understand the full history and structure of the universe. Eventually, even the cosmic microwave background, the remnant radiation from the Big Bang, will redshift beyond detectability, leaving future observers in a universe that appears much emptier and lonelier than it does today. This raises intriguing questions about the nature of cosmic knowledge. If future civilizations have access to only a small fraction of the universe's history and structure, will their understanding of the universe be fundamentally different from ours? Could there come a time when the true scale and age of the universe are forgotten, with distant galaxies and the cosmic microwave background being relegated to ancient myths or speculative theories? While this scenario is still billions of years in the future, it underscores the importance of the current era in cosmic history. We are living in a unique time when the expansion of the universe has not yet pushed distant galaxies beyond the observable horizon, giving us the ability to study the large-scale structure of the universe and reconstruct its history. The cosmic microwave background, in particular, provides a snapshot of the universe as it existed just 380,000 years after the Big Bang, allowing us to peer back in time and understand the conditions that led to the formation of galaxies and other cosmic structures. The expansion of the universe also has profound implications for its ultimate fate. While the accelerating expansion driven by dark energy suggests a future of continued expansion, other scenarios cannot be entirely ruled out. One of the key questions is whether dark energy is truly constant, or if it could change over time. If dark energy weakens or reverses its influence, the expansion of the universe could eventually slow down and reverse, leading to a contraction phase known as the Big Crunch. In this scenario, the universe would collapse back in on itself, potentially ending in a singularity much like the one that gave rise to the Big Bang. On the other hand, if dark energy becomes stronger over time, the universe could face a more dramatic fate known as the Big Rip. In this scenario, the expansion of the universe would accelerate to the point where it overwhelms all other forces, including gravity and the electromagnetic force. Galaxies, stars, and even atoms would be torn apart by the expansion of space, leading to the disintegration of all matter. This catastrophic end would leave the universe in a state of utter desolation, with no coherent structures remaining. There is also the possibility that the universe's expansion will continue indefinitely but at a steady or decelerating rate, leading to a big freeze, or heat death. In this scenario, the universe would continue to expand, but as stars burn out and galaxies move farther apart, it would become increasingly cold and empty. Over trillions of years, stars would exhaust their nuclear fuel, black holes would evaporate through a process known as Hawking radiation, and the universe would settle into a state of maximum entropy. In this final stage, no energy would be available to perform work, and the universe would effectively be dead, with no possibility of further change. These scenarios, while speculative, highlight the interplay between the expansion of the universe and the ultimate fate of all cosmic structures. The fate of the universe is inextricably linked to the behavior of dark energy and the fundamental forces that govern the cosmos. Understanding these forces is crucial not only for explaining the current state of the universe but also for predicting its long-term future. One of the tools that astronomers use to study the expansion of the universe is the redshift of light from distant galaxies. As the universe expands, the light from these galaxies is stretched, increasing its wavelength and shifting it toward the red end of the spectrum. This redshift provides a direct measure of how fast the universe is expanding and allows astronomers to estimate the distances to faraway galaxies. By comparing the redshifts of galaxies at different distances, astronomers can track the expansion history of the universe and determine whether it is speeding up or slowing down. The discovery of the universe's accelerating expansion was made in the late 1990s by two independent teams of astronomers, who were studying the redshifts of distant Type Ia supernovae. These supernovae are particularly useful for measuring cosmic distances because they have a consistent brightness, known as a standard candle. By comparing the observed brightness of these supernovae to their known intrinsic brightness, astronomers can calculate their distance from Earth. When the supernova teams plotted the distances of these objects against their redshifts, they found that the universe's expansion was accelerating, leading to the conclusion that some form of dark energy was driving this acceleration. This discovery was a major breakthrough in cosmology, as it provided the first direct evidence for the existence of dark energy. It also raised new questions about the nature of this mysterious force and its relationship to the other components of the universe, such as dark matter and ordinary matter. The acceleration of the universe's expansion also has implications for the age of the universe, as it suggests that the universe is older than previously thought. Current estimates place the age of the universe at around 13.8 billion years, based on observations of the cosmic microwave background and the distribution of galaxies. This age is consistent with the predictions of the Big Bang model, which describes the universe as having emerged from a hot, dense state in a rapid expansion known as inflation. The early universe was dominated by radiation and matter, with dark energy playing only a minor role. However, as the universe expanded and cooled, the influence of dark energy grew, eventually overtaking matter and radiation to become the dominant force driving the expansion. The study of the universe's expansion is also closely tied to the search for a unified theory of physics, which would reconcile the seemingly incompatible theories of quantum mechanics and general relativity. General relativity, which describes the behavior of gravity on large scales, has been incredibly successful at explaining the expansion of the universe and the behavior of cosmic structures. However, it breaks down when applied to the extreme conditions of the early universe, such as the singularity at the Big Bang or the interiors of black holes. Quantum mechanics, on the other hand, describes the behavior of particles on the smallest scales, and it has been remarkably successful in explaining the behavior of atoms, molecules, and subatomic particles. However, it does not easily incorporate the effects of gravity, which is described by general relativity. The search for a theory of quantum gravity, which would unite these two pillars of modern physics, is one of the major goals of theoretical physics. Such a theory would provide new insights into the nature of space, time, and the universe's expansion. One of the leading candidates for a theory of quantum gravity is string theory, which posits that the fundamental particles of nature are not point-like particles but rather tiny, vibrating strings that exist in multiple dimensions. String theory has the potential to explain the behavior of gravity on the smallest scales and to provide a unified framework for all the forces of nature. However, it remains a highly speculative and mathematically complex theory, with little direct experimental evidence to support it. Another approach to quantum gravity is loop quantum gravity, which attempts to quantize space and time themselves, treating them as discrete units rather than continuous quantities. This approach could offer new insights into the behavior of the universe near the Big Bang and the possible resolution of singularities in black holes. However, like string theory, loop quantum gravity remains a work in progress, with many open questions and challenges. The interplay between the expansion of the universe, dark energy, and the quest for a unified theory of physics highlights the deep connections between cosmology and fundamental physics. Understanding the nature of dark energy and the ultimate fate of the universe will require not only better observations but also new theoretical breakthroughs that go beyond our current understanding of space, time, and gravity. As we dive deeper into the mysteries of the universe's expansion, one must also consider the influence of inflation theory in the very early moments following the Big Bang. Inflation theory, proposed in the early 1980s, is a hypothesis that seeks to explain some of the universe's most perplexing features, such as its large-scale uniformity and the near-perfect flatness of space. According to this theory, a fraction of a second after the Big Bang, the universe underwent an incredibly rapid exponential expansion, growing by an unfathomable factor in a tiny amount of time. This inflationary period explains why the universe appears so homogeneous and isotropic on large scales. Without inflation, it would be difficult to account for how regions of the universe that are widely separated by vast distances could have come into thermal equilibrium, as they should not have had time to interact. Inflation solves this by positing that all regions of the observable universe were once much closer together before inflation stretched them apart. This means that even distant regions share a common history and were able to come into equilibrium before being separated by inflation. Inflation also provides an explanation for the flatness of the universe. In the context of general relativity, the curvature of space is determined by the total energy density of the universe. If the universe's energy density is exactly equal to a critical value, the universe will have zero curvature and be flat. If the energy density is greater than the critical value, the universe will have positive curvature, like the surface of a sphere, and if it is less, the universe will have negative curvature, like a saddle. Observations of the cosmic microwave background suggest that the universe is very close to being flat, which is a puzzling coincidence unless inflation is taken into account. During inflation, space expanded so rapidly that any initial curvature was smoothed out, just as the surface of a balloon becomes flatter as it inflates. This mechanism explains why the universe appears flat today, even though it could have started with any curvature. In this sense, inflation is a crucial part of our understanding of the universe's early history and its current large-scale structure. Inflation theory also provides a natural mechanism for the formation of cosmic structures such as galaxies and galaxy clusters. During inflation, quantum fluctuations in the fabric of space-time were stretched to macroscopic scales, creating small density variations in the otherwise uniform universe. These variations served as the seeds for the formation of galaxies, as regions with slightly higher density attracted more matter through gravity, eventually leading to the formation of large-scale structures. This process explains why the universe is not perfectly homogeneous but instead contains the rich tapestry of galaxies, clusters, and voids that we observe today. The inflationary model has been incredibly successful in explaining many of the observed features of the universe, but it is not without its challenges. One of the key questions is what caused inflation to start, and what brought it to an end. In most versions of inflation theory, inflation is driven by a hypothetical field known as the inflaton, which had a very high energy density in the early universe. As the universe expanded, the inflaton field's energy decreased, eventually causing inflation to end and the universe to transition into the hot, dense state described by the traditional Big Bang model. However, the precise nature of the inflaton field remains unknown, and there are many competing models of how inflation might have occurred. Some of these models predict that inflation might never truly end but instead continues in different regions of the universe, a scenario known as eternal inflation. In this model, while inflation ends in certain regions, allowing them to evolve into universes like ours, it continues indefinitely in other regions. This leads to the idea of a multiverse, where our observable universe is just one of many pocket universes that exist within a much larger and continually inflating multiverse. The concept of the multiverse is one of the most speculative and controversial ideas in modern cosmology. It arises naturally from certain inflationary models but also from other areas of theoretical physics, such as string theory. If the multiverse exists, it would mean that there are other universes with different physical laws, constants, and initial conditions, potentially leading to vastly different forms of matter, energy, and life. While the multiverse is an intriguing idea, it is also difficult to test or observe directly, as other universes would be causally disconnected from our own, lying beyond the observable horizon. The idea of a multiverse challenges our very notion of what constitutes the universe. Traditionally, the universe was thought to encompass everything that exists, but the multiverse suggests that our universe might be just one of many, each with its own distinct properties. This raises profound philosophical questions about the nature of reality and the limits of scientific inquiry. If other universes exist but are forever beyond our observational reach, can we truly consider them part of science, or do they belong to the realm of metaphysics? One of the most exciting aspects of studying the universe's expansion is that it forces us to confront these deep and sometimes unsettling questions. The more we learn about the cosmos, the more we realize how much remains unknown. The discovery of dark energy, the possibility of a multiverse, and the mysteries of inflation all point to the fact that our current understanding of the universe is incomplete. Yet, it is precisely this sense of mystery that drives scientific inquiry forward. As we look ahead to the future of cosmology, new technologies and observations promise to shed light on some of these mysteries. Next-generation telescopes, such as the James Webb Space Telescope and the upcoming Euclid and Nancy Grace Roman Space Telescopes, will allow astronomers to probe the distant universe with unprecedented precision, providing new data on dark energy, the expansion rate of the universe, and the formation of galaxies. These observations could help refine our understanding of inflation, dark energy, and the overall fate of the universe. In addition to observational advances, theoretical physics continues to explore new ideas that could revolutionize our understanding of the universe's expansion. Researchers are investigating alternative models of dark energy, such as quintessence, which posits that dark energy is not a constant but rather a dynamic field that changes over time. Other theories suggest that dark energy could be a manifestation of extra dimensions or that it could arise from modifications to general relativity. These ideas remain speculative, but they represent the cutting edge of research into one of the most profound mysteries of the cosmos. Ultimately, the study of the universe's expansion is a journey into the unknown. It forces us to confront the limits of our knowledge and the possibility that the universe is far stranger and more complex than we ever imagined. Yet, it is also a reminder of the incredible progress we have made in understanding the cosmos. From the discovery of the expanding universe to the realization that dark energy is driving its acceleration, each new discovery has opened up new avenues of exploration and raised new questions about the nature of reality. The expansion of the universe is not just a physical phenomenon, it is a window into the deepest mysteries of existence. It tells us that the universe is dynamic, evolving, and filled with possibilities that stretch beyond the limits of our imagination. As we continue to explore the cosmos, we are bound to encounter new surprises, new challenges, and new opportunities to expand our understanding of the universe and our place within it. As we continue to explore the mysteries surrounding the expansion of the universe, it's crucial to revisit some of the more technical aspects of cosmology that underpin our current understanding. One such element is the cosmological principle, a fundamental assumption that states that the universe is homogeneous and isotropic on large scales. In simple terms, this means that, when viewed on a sufficiently large scale, the universe looks the same in every direction and at every point, with no special locations or directions. This principle is foundational to the standard model of cosmology, and underlies many of the mathematical models we use to describe the expansion of the universe. The cosmological principle might seem like a trivial assumption, but it's crucial for simplifying the equations that govern the universe's expansion, particularly Einstein's field equations from general relativity. These equations describe how matter and energy influence the curvature of spacetime, which in turn dictates the motion of objects and the expansion of space itself. When applied to a homogeneous and isotropic universe, Einstein's equations simplify into a form known as the Friedmann equations, named after the Russian physicist Alexander Friedmann who first derived them in the 1920s. The Friedmann equations describe how the universe's expansion rate evolves over time, taking into account factors such as the density of matter, radiation, and dark energy. One of the key quantities in these equations is the Hubble parameter, which is a measure of the universe's expansion rate at a given moment. The Hubble parameter is named after Edwin Hubble, who discovered that distant galaxies are moving away from us, providing the first observational evidence for the expansion of the universe. The Hubble parameter is not a constant. It changes over time as the universe evolves. In the early universe, when matter and radiation were dominant, the expansion rate was much higher than it is today. As the universe expanded and cooled, the influence of matter and radiation decreased, while the effect of dark energy became more prominent, leading to the accelerated expansion that we observe today. The current value of the Hubble parameter is known as the Hubble constant, and measuring its precise value has been one of the major goals of modern cosmology. However, determining the exact value of the Hubble constant has proven to be surprisingly difficult. There are two main methods for measuring the Hubble constant, and they yield slightly different results, leading to what is known as the Hubble tension. One method involves observing distant galaxies and supernovae to directly measure their redshifts and distances, while the other method relies on data from the cosmic microwave background to infer the universe's expansion rate in the early universe. The discrepancy between these two measurements suggests that there may be something missing from our current understanding of cosmology, or that new physics may be required to reconcile the two values. The Hubble tension has sparked considerable debate and research in the cosmology community. Some scientists propose that the discrepancy could be due to systematic errors in one or both measurement methods. Others suggest that the tension could be a sign of new physics, such as modifications to the properties of dark energy, changes to the behavior of dark matter, or even the existence of previously unknown particles or forces. Resolving the Hubble tension is one of the most important open questions in modern cosmology, as it could lead to a deeper understanding of the universe's expansion and the fundamental forces that govern its behavior. Another key concept related to the universe's expansion is the notion of the scale factor, which is a dimensionless quantity that describes how the size of the universe changes over time. The scale factor is normalized to a value of 1 at the present time, and its value decreases as we look back into the past. For example, at the time of the Big Bang, the scale factor was effectively 0, meaning that the universe was compressed into an infinitesimally small volume. As the universe expanded, the scale factor increased, and it continues to grow as the universe expands today. The evolution of the scale factor is determined by the relative contributions of matter, radiation, and dark energy to the overall energy density of the universe. In the early universe, radiation was the dominant component, and the scale factor grew relatively slowly. As the universe cooled and matter became more dominant, the expansion rate increased, but it wasn't until dark energy began to dominate that the expansion of the universe began to accelerate. The interplay between these different components of the universe's energy density is crucial for understanding its past and future evolution. For instance, if dark energy were not present, the universe's expansion would eventually slow down and possibly reverse, leading to a big crunch, where the universe collapses back in on itself. Conversely, if dark energy continues to dominate, and its effects become stronger over time, the universe could undergo a big rip, where the expansion accelerates so rapidly that galaxies, stars, and even atoms are torn apart. While the Big Rip scenario remains speculative, it illustrates the profound implications that dark energy has for the ultimate fate of the universe. The current consensus, based on observations of the cosmic microwave background, galaxy surveys, and supernovae, is that the universe will continue expanding at an accelerated rate indefinitely. This leads to a cold, dark, and empty future known as the heat death of the universe, where all stars eventually burn out, galaxies drift apart, and the universe becomes a vast, empty expanse with only faint remnants of its former glory. This bleak picture of the universe's future stands in stark contrast to its fiery beginnings in the Big Bang. Yet, it is the natural consequence of the universe's expansion and the role of dark energy in driving that expansion. While the heat-death scenario may seem depressing, it is also a testament to the power of modern cosmology to make predictions about the far future based on current observations and theoretical models. As we reflect on the mysteries of the universe's expansion, it is worth considering the role of observational cosmology in advancing our understanding. From Hubble's discovery of the expanding universe to the precise measurements of the cosmic microwave background by satellites such as COBE, WMAP, and Planck, our ability to observe the universe has revolutionized our understanding of its history and evolution. Each new observation provides clues about the nature of dark energy, the behavior of matter and radiation, and the fundamental forces that shape the cosmos. In recent years, one of the most exciting developments in observational cosmology has been the detection of gravitational waves, ripples in space-time caused by the acceleration of massive objects such as black holes and neutron stars. Gravitational wave astronomy is a new and rapidly growing field that promises to provide new insights into the expansion of the universe and the nature of its most extreme objects. By observing gravitational waves from distant cosmic events, astronomers can probe the universe in ways that were previously impossible, opening up new avenues for understanding its expansion and ultimate fate. As we continue to observe the universe and refine our theoretical models, new discoveries are sure to emerge that challenge our current understanding and push the boundaries of knowledge. The expansion of the universe is not just a physical phenomenon, it is a cosmic story that continues to unfold, with each new observation adding another chapter to the tale. From the earliest moments of the Big Bang to the far future of the universe, the study of cosmic expansion provides a window into the deepest mysteries of existence and our place within the cosmos. To delve deeper into the complexities of the universe's expansion, it's essential to examine the historical context and evolution of cosmological thought. The story begins with the ancient Greeks, who speculated about the nature of the cosmos and the heavens. Philosophers like Aristotle and Ptolemy proposed geocentric models, where the Earth was at the center of the universe, surrounded by celestial spheres. These ideas dominated for centuries, shaping humanity's understanding of the cosmos. The revolutionary shift in cosmological thinking began in the 16th century with the work of Nicholas Copernicus, who proposed the heliocentric model, placing the Sun at the center of the solar system. This radical idea laid the groundwork for future astronomers, including Johannes Kepler and Galileo Galilei, who provided empirical evidence that supported the heliocentric model. Kepler's laws of planetary motion and Galileo's observations of celestial bodies through the telescope challenged long-held beliefs and marked the dawn of modern astronomy. By the 19th century, the study of the universe began to take on a more scientific approach, thanks in part to the work of Isaac Newton. His laws of motion and universal gravitation provided a mathematical framework for understanding celestial mechanics. Newton's insights allowed astronomers to analyze the motion of planets and stars with greater precision, leading to a more accurate understanding of the universe's structure. However, the concept of an expanding universe did not emerge until the 20th century. Albert Einstein's theory of general relativity, published in 1915, fundamentally changed our understanding of gravity and its relationship to spacetime. Einstein proposed that massive objects warp the fabric of spacetime, causing objects to follow curved paths. This revolutionary theory opened the door to new possibilities in cosmology, suggesting that the universe could be dynamic rather than static. Initially, Einstein believed in a static universe and introduced the cosmological constant, a term added to his equations to counteract gravitational attraction and maintain a steady state. However, this view was challenged when astronomer Edwin Hubble conducted his groundbreaking observations in the 1920s. Hubble discovered that distant galaxies exhibited redshift, indicating they were moving away from us. This observation provided compelling evidence that the universe was indeed expanding. Hubble's findings were monumental, leading to the formulation of Hubble's law, which states that the velocity at which a galaxy recedes from an observer is proportional to its distance from that observer. This law not only confirmed the expansion of the universe but also provided a method to estimate its age. By extrapolating back in time, cosmologists estimated that the universe began around 13.8 billion years ago, a moment known as the Big Bang. The implications of the expanding universe were profound. It suggested that the universe had a finite beginning and would continue to evolve. This concept posed philosophical questions about the nature of existence and the ultimate fate of the universe. The notion of a dynamic, evolving cosmos was a radical departure from the static models of the past. As cosmology progressed, researchers sought to understand the forces driving the universe's expansion. The discovery of cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson provided a significant piece of evidence supporting the Big Bang theory. This faint afterglow, a remnant of the hot, dense state of the early universe, offered insights into its early conditions and evolution. The cosmic microwave background serves as a snapshot of the universe approximately 380,000 years after the Big Bang, revealing the seeds of structure that would eventually give rise to galaxies and clusters. In the following decades, cosmologists developed the hot Big Bang model, which describes the universe's evolution from a hot, dense state to its current expansion. This model incorporated various components, including baryonic matter, dark matter, and dark energy. The latter, a mysterious force thought to permeate all of space, emerged as a key player in understanding the universe's accelerating expansion. The late 1990s marked a turning point in cosmology with the discovery of dark energy. Two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, observed distant supernovae and found that the universe's expansion was accelerating rather than slowing down as previously expected. This shocking revelation prompted a re-evaluation of the cosmological model, leading to the conclusion that dark energy constitutes about 68% of the universe's total energy density. Despite significant advancements in our understanding of the universe's expansion, dark energy remains one of the most profound mysteries in contemporary science. Its nature and origin are still largely unknown, and numerous theories have been proposed to explain its behavior. Some scientists speculate that dark energy could be a cosmological constant, a property of empty space itself. Others suggest that it might be a dynamic field, evolving over time and leading to a more complex understanding of the universe's fate. As cosmologists grapple with the implications of dark energy, they continue to refine their observational techniques and theoretical models. Projects like the Large Hadron Collider and various space-based observatories aim to probe the fundamental forces that govern the cosmos. Advancements in technology have enabled astronomers to study distant galaxies with unprecedented detail, providing insights into the universe's structure and evolution. In recent years, the concept of inflation has also gained traction as a potential explanation for the uniformity and isotropy of the universe. Inflation proposes a rapid expansion of the universe during its earliest moments, smoothing out any irregularities and leading to the homogeneous universe we observe today. While inflationary theory has provided valuable insights, it too remains a subject of active research and debate within the scientific community. Furthermore, the role of quantum mechanics in cosmology has emerged as an intriguing area of study. The interplay between quantum fluctuations and cosmic expansion raises fundamental questions about the nature of reality. Some theorists propose that quantum effects could give rise to the universe's initial conditions, leading to the observed large-scale structure. The marriage of quantum mechanics and cosmology may hold the key to unlocking further mysteries of the universe. As we stand on the precipice of new discoveries, the expansion of the universe invites us to ponder profound questions about our existence and the nature of reality. What lies beyond the observable universe? Are there other dimensions or realms of existence that we have yet to discover? How will the universe evolve in the far future? These questions ignite our curiosity and drive our pursuit of knowledge. Ultimately, the mysteries of the universe's expansion are not merely academic. They are deeply intertwined with our understanding of ourselves and our place in the cosmos. As we seek to unravel these mysteries, we embark on a journey that transcends time and space, connecting us to the fundamental truths of existence. The study of the universe's expansion continues to evolve, driven by the tireless efforts of scientists, astronomers, and researchers across the globe. Each new discovery brings us closer to a comprehensive understanding of the cosmos, shedding light on the intricate tapestry of space and time. As we venture into the unknown, we are reminded that the universe is not just a distant expanse of stars and galaxies. It is a dynamic, ever-evolving entity that challenges our perceptions and inspires our imagination. The expansion of the universe is a captivating and multifaceted phenomenon that lies at the heart of modern cosmology. From its inception in the Big Bang to its current accelerated expansion driven by dark energy, the universe's journey is one of mystery, wonder, and discovery. As we continue to explore the cosmos, we remain humble in the face of its complexities, recognizing that there is still much to learn. The expansion of the universe serves as a testament to the enduring human spirit, a reminder of our innate curiosity and desire to understand the world around us. With each new discovery, we move closer to unraveling the mysteries of the cosmos and deepening our connection to the universe that we inhabit. As we delve further into the intricacies of the universe's expansion, it's essential to explore the implications of these discoveries on our understanding of the cosmos. The expansion poses fundamental questions about the universe's structure, composition, and eventual fate. One of the most intriguing aspects of the universe's expansion is its impact on cosmic structures. Galaxies are not uniformly distributed throughout the universe. Instead, they are organized into vast filaments and clusters, separated by enormous voids. This large-scale structure is a result of gravitational interactions and the distribution of dark matter. As the universe expands, gravitational forces work to pull galaxies closer together, forming clusters, while the expansion itself drives them apart over vast distances. This intricate dance of attraction and repulsion shapes the universe's architecture, revealing a complex interplay between expansion and gravity. Observations have shown that the universe is expanding uniformly in all directions, a phenomenon known as isotropy. This uniformity is a critical aspect of cosmological models, as it suggests that the laws of physics are consistent throughout the cosmos. However, deviations from this isotropy can lead to fascinating insights into cosmic history. Anomalies in the cosmic microwave background radiation, for example, provide clues about the early universe's density fluctuations, influencing galaxy formation and the evolution of cosmic structures. The concept of cosmic inflation, introduced by Alan Guth in the early 1980s, offers a theoretical framework to explain these observations. Inflation posits that the universe underwent a rapid exponential expansion during its earliest moments, smoothing out irregularities and leading to the homogeneous and isotropic universe we observe today. This brief period of inflation can account for the uniformity of the cosmic microwave background, as well as the large-scale structure of the universe. Inflation also raises intriguing possibilities regarding the multiverse theory, which suggests that our universe may be just one of many. In this framework, different regions of space could experience varying rates of inflation, leading to distinct physical laws and properties. While the multiverse remains a speculative idea, it challenges our understanding of reality and the nature of existence itself. If our universe is just one of many, what does that imply about our significance within the grand tapestry of the cosmos? As we contemplate these cosmic mysteries, we must also consider the ultimate fate of the universe. The question of whether the universe will continue to expand indefinitely or eventually collapse under the influence of gravity is a central topic in cosmology. Current observations indicate that the universe's expansion is accelerating, driven by dark energy. This raises the possibility of scenarios such as the Big Freeze, where galaxies drift apart over trillions of years, leading to a cold and desolate cosmos. In this scenario, stars will eventually burn out, and galaxies will become isolated, resulting in a universe filled with dark emptiness. Conversely, some theories propose that the universe could experience a Big Crunch, a scenario in which the expansion eventually halts and reverses, leading to a collapse back into a singularity. However, current evidence strongly favors the accelerating expansion driven by dark energy, making the Big Freeze scenario more likely. Another intriguing possibility is the Big Rip, a scenario in which the expansion of the universe accelerates to the point that it tears apart galaxies, stars, and even atoms. This hypothesis raises profound questions about the nature of time, space, and the fundamental forces of the universe. If the Big Rip were to occur, it would signify an end to the universe as we know it, leading to a state where all structures are obliterated. These scenarios not only challenge our understanding of the cosmos but also evoke philosophical inquiries about existence and purpose. The contemplation of cosmic destinies invites us to reflect on our place in the universe and the transient nature of life itself. Are we mere observers in a vast and indifferent cosmos, or do we hold a deeper significance within the grand narrative of existence? These existential questions intertwine with scientific inquiry, prompting a dialogue between cosmology, philosophy, and the human experience. As we continue to probe the mysteries of the universe, advancements in technology and observational techniques play a crucial role. The construction of powerful telescopes, both ground-based and space-based, allows astronomers to explore distant galaxies and observe cosmic phenomena in unprecedented detail. Projects like the James Webb Space Telescope aim to uncover the universe's secrets by peering back in time to observe the formation of stars and galaxies in the early universe. By capturing the faint light emitted by ancient celestial bodies, researchers hope to gain insights into the conditions that led to the universe's expansion and evolution. Additionally, gravitational wave astronomy has emerged as a groundbreaking field, providing new avenues for understanding cosmic events such as the merging of black holes and neutron stars. The detection of gravitational waves opens a new window into the universe, revealing phenomena that were previously elusive. By studying these ripples in space-time, scientists can learn about the dynamics of massive celestial bodies and their influence on the universe's expansion. As we look to the future, the pursuit of knowledge about the universe's expansion and its mysteries is more vital than ever. Collaborative efforts among scientists across disciplines, including physics, astronomy, and cosmology, are essential for unraveling the complexities of the cosmos. The quest for understanding is not merely an intellectual endeavor, it is a testament to humanity's curiosity and desire to explore the unknown. In this pursuit, we are reminded that the universe is a vast and intricate tapestry woven from the threads of time, space, and matter. Each discovery adds a new layer to our understanding, revealing the interconnectedness of all things. The universe's expansion is not just a scientific phenomenon, it is a reflection of our own journey of exploration and self-discovery. As we navigate the uncharted territories of cosmic knowledge, we must remain humble in the face of the vast unknown. The mysteries of the universe beckon us to ask questions, challenge assumptions, and seek deeper truths. With each revelation, we come closer to understanding our place in the cosmos and the fundamental nature of existence. The expansion of the universe serves as a reminder that we are part of something far greater than ourselves. It connects us to the stars, the galaxies, and the intricate web of cosmic phenomena. The beauty and complexity of the universe inspire awe and wonder, igniting our imagination and fueling our desire to explore the cosmos. The universe's expansion is a captivating and multifaceted phenomenon that transcends the boundaries of science and philosophy. From the earliest moments of the Big Bang to the mysteries of dark energy and the future of cosmic evolution, the journey of understanding is ongoing. As we continue to unravel the mysteries of the universe, we are reminded of our place within this grand cosmic narrative and the significance of our quest for knowledge. The expansion of the universe invites us to explore, discover, and dream as we venture into the unknown, seeking to uncover the profound truths that lie beyond the stars. Continuing our exploration of the universe's expansion, we can further discuss the scientific principles and groundbreaking theories that underpin our understanding of this vast phenomenon. The expansion of the universe is not just a fact. It represents a dynamic process influenced by various factors, including dark energy, the distribution of matter, and the laws of physics. One of the foundational pieces of evidence supporting the expansion of the universe comes from the observation of redshift in distant galaxies. When light from these galaxies reaches us, it is shifted toward the red end of the spectrum, indicating that they are moving away from us. This redshift is a consequence of the Doppler effect, which states that the wavelength of light increases as an object moves away from an observer. The further away a galaxy is, the more pronounced its redshift, suggesting that the universe is expanding uniformly in all directions. The discovery of redshift was revolutionary, fundamentally changing our understanding of the cosmos. Edwin Hubble's observations in the 1920s provided critical evidence for this expansion. Hubble formulated Hubble's law, which posits that the velocity at which a galaxy recedes is proportional to its distance from us. This correlation implies that the universe itself is stretching, with galaxies moving away from each other over time. Hubble's findings laid the groundwork for the Big Bang theory, which posits that the universe originated from an extremely hot and dense state approximately 13.8 billion years ago. This theory suggests that as the universe expanded, it cooled, allowing matter to form and coalesce into the stars and galaxies we observe today. The Big Bang is not merely an explosion but rather a rapid expansion of space itself, shaping the universe's structure and composition. However, the expansion of the universe is not a straightforward process. It is influenced by various forms of energy and matter, including dark matter and dark energy. Dark matter, which makes up about 27% of the universe, exerts gravitational forces, helping to bind galaxies and clusters together. Though we cannot see dark matter directly, its presence is inferred from its gravitational effects on visible matter. This elusive substance plays a critical role in the formation of large-scale structures in the universe. On the other hand, dark energy, which constitutes about 68% of the universe, is responsible for the acceleration of cosmic expansion. This mysterious force opposes gravitational attraction and acts as a sort of anti-gravity. The nature of dark energy remains one of the most profound mysteries in cosmology. While several theories have been proposed, including the cosmological constant introduced by Albert Einstein, the true nature of dark energy is still largely unknown. The interplay between dark matter and dark energy creates a complex cosmic landscape. Understanding how these components affect the universe's expansion is essential for developing a comprehensive cosmological model. Researchers utilize a variety of observational techniques, including the study of supernovae, gravitational lensing, and the cosmic microwave background, to probe the properties of dark energy and its implications for the future of the universe. As we investigate the mysteries surrounding the universe's expansion, we must also confront some philosophical questions that arise from our scientific inquiries. The concept of an expanding universe challenges our intuitive notions of space and time. If the universe is continually expanding, what does that mean for our understanding of causality and the nature of existence? Are we mere observers in a vast and indifferent cosmos, or do we play a role in shaping its destiny? Furthermore, the expansion of the universe raises questions about the nature of time itself. The theory of relativity, formulated by Einstein, suggests that time is not a fixed entity but is intertwined with space, forming a four-dimensional fabric that we refer to as space-time. In this framework, the expansion of the universe influences the passage of time, leading to a deeper understanding of how we experience reality. For example, as galaxies move away from us, the light from these distant objects takes longer to reach us, creating a sort of time lag. This phenomenon allows astronomers to observe the universe's history, essentially looking back in time as they gaze at ancient galaxies and cosmic events. The concept of space-time leads us to consider the implications of an expanding universe on our perception of reality. In an ever-expanding cosmos, the distances between celestial objects increase, altering our understanding of cosmic scale and the interconnectedness of the universe. This realization fosters a sense of humility in the face of the vastness of space, reminding us of our relatively insignificant position within the grand scheme of the cosmos. As we explore the universe's expansion further, we encounter the concept of cosmic inflation, which serves as a critical theoretical framework for understanding the early moments of the universe. Inflation proposes that the universe experienced an exponential expansion during the first few moments after the Big Bang, effectively stretching and smoothing out the fabric of spacetime. This rapid expansion addressed several long-standing issues in cosmology, such as the horizon problem and the flatness problem. The horizon problem refers to the question of why different regions of the universe appear to have the same temperature and density despite being separated by vast distances. Inflation provides a solution by suggesting that these regions were once in close proximity before being rapidly expanded beyond each other's reach. Consequently, they retained a uniform temperature, leading to the observed isotropy of the cosmic microwave background radiation. The flatness problem arises from observations that the universe appears to be spatially flat, with the density very close to the critical density required for a balanced geometry. Inflation predicts that any initial curvature would be diluted as the universe expands, resulting in a flat geometry. This prediction aligns with current observations, further supporting the inflationary model. Moreover, inflation introduces the idea of quantum fluctuations during the rapid expansion phase. These tiny variations in density could seed the formation of galaxies and large-scale structures as the universe continued to evolve. The legacy of inflation extends to our understanding of cosmic structure formation, offering a coherent explanation for the distribution of galaxies we observe today. Yet, despite the successes of the inflationary model, it raises additional questions and challenges. For instance, what mechanism drives inflation, and what caused the rapid expansion? Various models have been proposed, including scalar fields and hypothetical particles known as inflatons, but definitive answers remain elusive. This ongoing quest for understanding continues to inspire research in theoretical physics and cosmology. As we consider the future of the universe, we must also confront the implications of its expansion on our existence. The accelerating expansion driven by dark energy raises existential questions about the long-term fate of the cosmos. If the current trend continues, the universe may evolve into a state where galaxies drift apart, leaving behind isolated remnants. This scenario, known as the Big Freeze, suggests a universe in which stars eventually burn out and cosmic structures fade into darkness. In the Big Freeze scenario, the universe would become increasingly cold and empty, resulting in a distant future devoid of the vibrant cosmic interactions we observe today. Stars would exhaust their nuclear fuel, and black holes would become the last bastions of matter. Over unimaginable timescales, even black holes might evaporate through a process known as Hawking radiation, leaving behind a universe that is almost entirely dark and devoid of complexity. Conversely, the potential for a Big Rip scenario, where the expansion accelerates to the point of tearing apart galaxies and even atomic structures, presents a different perspective on the universe's fate. This catastrophic end would signify the ultimate unraveling of the cosmos, a scenario that challenges our understanding of physical laws and the very nature of reality. If such an event were to occur, it would raise profound questions about the nature of time and existence itself, prompting philosophical reflections on the significance of our fleeting lives in the vast expanse of an ever-changing universe. In contemplating the universe's expansion and its implications, we must also acknowledge the role of technology and scientific exploration in shaping our understanding. Advancements in observational tools, such as the upcoming missions of the James Webb Space Telescope, promise to revolutionize our ability to study distant galaxies, dark energy, and the cosmic microwave background radiation. By probing the far reaches of space, we can uncover new insights into the universe's early history and the mechanisms driving its expansion. Additionally, the burgeoning field of gravitational wave astronomy offers a new dimension to our understanding of the cosmos. The detection of gravitational waves from events such as black hole mergers provides unique opportunities to investigate the nature of space-time and the dynamics of massive celestial bodies. These observations could shed light on the interactions between gravitational forces and the expansion of the universe, deepening our understanding of the cosmos. As we journey through the mysteries of space and the expansion of the universe, we are reminded of the interconnectedness of all things. The cosmos is not merely a collection of isolated objects but a vast, dynamic system governed by fundamental laws of physics. Each discovery, each revelation, contributes to the intricate tapestry of knowledge that shapes our understanding of the universe and our place within it. In conclusion, the expansion of the universe is a profound and multifaceted phenomenon that challenges our perceptions of reality and existence. From the early moments of the Big Bang to the mysteries of dark energy and the implications for the universe's fate, our exploration of cosmic expansion invites us to ponder our significance in the grand scheme of the cosmos. As we continue to unravel the mysteries of the universe, we embark on a journey that transcends the boundaries of science and philosophy, igniting our curiosity and inspiring future generations to seek answers to the questions that lie beyond the stars. This endeavor is not merely an intellectual pursuit, it is a testament to humanity's innate desire to explore, understand, and connect with the cosmos. Each question we ask, each mystery we unravel, brings us closer to the profound truths that govern our existence and the universe at large. The expansion of the universe reminds us that we are part of a grand narrative, a story that is constantly unfolding and inviting us to participate in its exploration. As we stand on the precipice of discovery, we must embrace the uncertainties and complexities of the cosmos. The universe is an ever-evolving entity, and our understanding will continue to grow as we seek to uncover its secrets. Through collaboration, innovation, and a shared passion for exploration, we can forge a path toward a deeper understanding of the universe's expansion and its mysteries. The journey is far from over, it is just beginning. As we gaze into the night sky, we are reminded that each star, each galaxy, carries within it a story waiting to be told. The mysteries of space beckon us to inquire, to ponder, and to dream. In this pursuit, We are united by our shared curiosity and wonder, as we continue to explore the vast expanse of the cosmos and the enigmatic expansion that defines it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.